Welcome to Copilot Podcasts. A mathematical earthquake just shook the foundations of number theory, and you're about to learn why it matters. Today, we're diving into one of the most significant mathematical breakthroughs of our time, the proof of the Riemann Hypothesis. And joining me is our resident mathematics expert who's been analyzing this groundbreaking proof. What's your take on this?
Well, this is absolutely monumental. The Clay Mathematic Institute just received a proof that could change mathematics forever. What makes this particularly fascinating is the approach. It uses something called a Gaussian, non-Gaussian partition.
Okay, before we dive deeper, can you break down what that means for our listeners?
Sure. The proof essentially divides prime numbers into two groups, Gaussian primes and non-Gaussian primes. The Gaussian group includes primes that equal 3 when divided by 4, plus the number 2. The non-Gaussian group includes primes that equal 1 when divided by 4.
That seems surprisingly simple for such a complex problem.
That's actually what makes it brilliant. The proof establishes 5 key lemmas. Think of them as building blocks.
Can you walk us through these lemmas?
The first is a Gaussian truncated lower bound. It shows that the Gaussian prime contributions maintain a robust size.
And what about the non-Gaussian part?
That's where the second lemma comes in. It proves that the non-Gaussian contributions are too weak to balance things out.
Interesting. What's the third lemma about?
The third lemma deals with phase nondegeneracy. It basically shows that certain mathematical waves can't cancel each other out completely.
That sounds crucial to the whole proof.
Absolutely. The fourth and fifth lemmas handle the technical details, controlling the tails of our sums and lifting our results to the full picture.
You know what's fascinating about this? It's like dividing a huge problem into manageable pieces.
Exactly. And that's what makes this proof so elegant. It creates a contradiction that can't be resolved.
Can you explain how that contradiction works?
The proof shows that if there were any zeros off the critical line, the Gaussian part would be larger than the sum of the other parts. But that's impossible under the assumptions of the Riemann hypothesis, so no such zeros can exist.
That's incredibly clever. It reminds me of proving something is impossible by showing it leads to an absurd result.
Precisely. And what's remarkable is how the proof uses relatively elementary concepts to tackle this complex problem.
You mentioned the Clay Mathematic Institute earlier. Why is this such a big deal for them?
Well, the Riemann hypothesis was one of their Millennium Prize problems, with a $1 million reward for solving it.
$1 million? That's quite an incentive.
Yes, but the real value is in what this means for mathematics. The Riemann hypothesis connects to countless other mathematical problems.
How so?
It's like a keystone. Proving it true unlocks new approaches to many other mathematical challenges.
That's fascinating. And this partition approach, it seems like such a creative way to tackle the problem.
Sometimes the best solutions come from looking at problems in a completely new way.
It's almost like dividing a huge task into smaller, more manageable pieces.
Exactly. And each piece reveals something important about the whole problem.
Let's talk about the technical aspects. The proof uses something called the Euler product log derivative.
Yes, it's a way of expressing the relationship between prime numbers and the zeros of the zeta function.
And this is where the partition comes in.
Right. By splitting the primes into two groups, we can analyze their contributions separately.
The proof mentions something about major arcs. What are those?
Those are special regions where the mathematical waves might align in problematic ways.
And the proof shows these aren't an issue?
Exactly. The fourth lemma proves these regions are too small to affect the overall result.
It's amazing how all these pieces fit together.
That's the beauty of mathematics. When a proof works, everything aligns perfectly.
What happens next? How will this affect other areas of mathematics?
Well, now mathematicians can use this result to solve other problems that depend on the Riemann hypothesis being true.
So it's like unlocking a whole new set of mathematical tools?
Exactly. And who knows what other mathematical mysteries these tools might help us solve.
The proof also seems to demonstrate something about problem solving in general.
Yes, sometimes the key to solving a complex problem is finding the right way to break it down.
And in this case, that meant looking at prime numbers in a new way.
Precisely. The partition approach revealed patterns that weren't visible before.
What do you think is the most elegant part of this proof?
I'd say it's how it uses relatively simple concepts to prove something so profound.
Like using basic arithmetic to solve a complex puzzle?
That's a great analogy. It shows that sometimes the most powerful solutions are also the most elegant.
This has been absolutely fascinating. Any final thoughts on the significance of this proof?
This proof isn't just about solving a mathematical puzzle, it's about opening new doors in our understanding of numbers.
And it all started with dividing some prime numbers into two groups.
Sometimes the biggest breakthroughs come from the simplest ideas.
Well, that brings us to the end of today's episode of Copilot Podcasts. Remember, even the most complex problems can be solved by finding the right way to break them down.
And sometimes, that solution has been hiding in plain sight all along.
Thanks for joining us on this mathematical journey. Until next time.